The purpose of this video presentation is to demonstrate the MSC process for the Southwest Nova Scotia and Bay of Fundy herring fishery, specifically how the closed-loop simulations are used to test the performance of candidate management procedures and to familiarise the group with the typical outputs of an MSE analysis. In our last meeting in May, we discussed the development of operating models and candidate management procedures, MPs for short. With our set of operating models, we can now start testing the MPs using closed-loop simulations. 3 inputs are required for the simulations. First, the operating models, presented in the last meeting. Second, the candidate management procedures. These are the rules for providing the TAC advice in each year. And third, a set of performance metrics that are used to evaluate whether an MP is likely to meet the management objectives. We will briefly discuss each of these inputs in the next few slides. But first we'll have a quick recap of the closed-loop simulation process and how it is used to test the performance of the MPs. The primary input for the closed-loop simulations is the operating model, or OM. The OM describes the historical dynamics of the fishery and is built by fitting a conditioning model to the fishery data. Because there are often many uncertainties associated with the fishery data and the assumptions of the conditioning model, for example the life history parameters such as natural mortality, there are often several OMs that are considered plausible hypotheses of the dynamics and status of the stock. The MSE process involves running closed-loop simulations for each operating model. The OM uses a population dynamics model to reconstruct the historical fishery. Simulated fishery data is generated by applying an observation model with observation error and uncertainty designed to replicate the real situation to the data generated by the model. For this fishery, the primary data that is used for management is the index from the acoustic survey. The simulation model generates a simulated index in the future projections that has the same statistical properties as the acoustic index used in the OM conditioning. A candidate management procedure is then applied to the simulated data. The MP processes the simulated data according to its specific rules and returns a TAC recommendation for the next year. Next, the TAC is implemented into the fishery dynamics. This takes place with the implementation model, which determines if the recommended TAC is implemented perfectly or perhaps subject to some implementation error, which results in the actual catches being higher or lower than the recommended TAC. The final step involves closing the loop. That is, the TAC recommended by the MP is applied back into the population dynamics model and the model is moved forward 1 year. The process is then repeated for the next year, with the fishery data being generated from the updated population dynamics model, the MP applied again to the next year of data, the TAC implemented into the fishery, and the model updated again for the next year. The fishery information, for example the catch, abundance, age composition, and other information generated by the model is saved in each time step. At the end of the projection period, the performance of the management procedures can be evaluated. This is done by summarizing the key statistics of the population dynamics model, such as the spawning stock biomass relative to the reference points and the simulated catches that were taken in the model. The closed-loop process is then repeated for each candidate management procedure, resulting in summary performance statistics for each MP for this specific operating model. The process of testing each MP is then repeated for each operating model. By comparing the performance of the MPs against a set of management objectives, we can determine which MP is most robust to the uncertainty captured by the set of OMs and most likely to result in the desired management outcomes. No single OM is a definitive representation of the real fishery system. Rather, a range of operating models are established with the aim of encompassing a plausible set of fishery scenarios. These OMs are referred to as reference OMs. 4 principal axes of uncertainty are considered in the reference OMs. There are 3 alternative hypotheses for the natural mortality rate, 2 assumptions for patterns in growth in the future years, 2 assumed levels of stock resilience in terms of the stock-recruit relationship, and 2 scenarios for the catch data used to condition the OMs. A full factorial analysis of the levels in these factors results in 24 reference set OMs for the herring MSC. For example, reference set OM1 is a model where the natural mortality rate is assumed to be 0.35 for all ages. Future growth is assumed to be the average of the last 3 historical years. The stock is assumed to have a high resilience with a steepness of 0.95, and the weir catches were not included in the operating model conditioning, with the population assumed to be in an unfished state in 1967. A management procedure is a set of rules that describe how a management recommendation, in this case a total allowable catch, is determined from fishery data. The primary data for this fishery is the acoustic survey of the spawning stock. The acoustic survey is used as a relative index of abundance, with the trend in abundance inferred from the acoustic survey used to set the total allowable catch limit in each year. In the next few slides, we'll develop a couple of example candidate management procedures that use this data to calculate a TAC. It is important to note that there are countless different MPs that could be constructed to produce a TAC recommendation from the acoustic survey index. Any clearly defined set of rules can be proposed and evaluated using closed-loop simulation, and interested stakeholders are encouraged to develop their own candidate MPs to be included in the analysis. The first example candidate management procedure is designed as an approximation of the harvest control rule currently in place for the herring fishery. We'll refer to it here as a status quo MP. This MP has two control points. The first is defined as the average index from 2005 to 2010, the grey dashed line on the plot. If the index goes below this point, the TAC is set to a minimum of 35,000 tonnes. The second control point is the mean index from 1999 to 2004, shown on the plot as a dashed black line. If the index goes above this point, the TAC is set to a maximum of 75,000 tonnes. When the index is between the control points, the TAC is determined by the sloped line in the harvest control rule. In the next few slides, we'll show an example of this MP in action. The plot on the left side is a spawning stock biomass that was estimated in the conditioning of this operating model. This trajectory in spawning stock biomass is reproduced in the simulation model. The plot on the right with the blue line is the acoustic index. The dotted and dashed lines show the two control points. The plots have now been updated to show the first projection year. The black triangle is the spawning stock biomass generated by the simulation model. The blue triangle is a simulated acoustic index. It follows the spawning biomass and shows a slight increase from the previous year. The index for the first projection year has a value of 245,000. Because this is below the control point of 317,000, the TAC is set to the minimum value of 35,000 tonnes. This TAC is implemented into the population dynamics model, and the model is updated one time step. The plots have now been updated for the second projection year. In this case, the simulated spawning stock biomass increased again by a small amount. The acoustic index increased as well, but as it is still below the control point, the TAC remains at 35,000 tonnes. The plots have now been updated for the third projection year. Here the spawning stock biomass increases a small amount for the previous year, while due to observation error the index increases by a larger amount. As the index is now above the first control point, the TAC is calculated from the harvest control rule and set at just over 41,000 tonnes. The second example MP is similar to the one presented in the last online meeting. It is a simple index targeting MP and uses the same target and limit control points. If the observed index is above the target, the TAC is increased by 5%. If the index is below the target, the TAC is reduced by 5%. And if the index is below the limit control point, the TAC is reduced by 10%. This MP also has a minimum and maximum. In this case, a maximum TAC of 80,000 tonnes and a minimum of 20,000. Unlike the previous example, where the MP used the index directly, this MP applies a smoother to the acoustic index. The third example MP is a modified version of the previous one. In this case, the TAC is adjusted up and down by 10% and down by 20% when the index is below the limit. The fourth example MP is another modification of index target MP number 1. In this case, the adjustment to the TAC remains the same, but the control point for the target index has been set to 300,000 and the limit to 200,000. Finally, we have two reference MPs. A simple MP with a TAC is fixed at a constant value of 75,000 tonnes, independent of the acoustic index, and an MP where there is no fishing at all. It is useful to include the no fishing MP in the MSE as it allows us to understand how the population is expected to behave in the absence of fishing. This provides useful context for interpreting the performance of the other management procedures. We've taken the feedback received from the group and defined a preliminary list of 4 MSC objectives. First, to rebuild the spawning stock biomass to the upper stock reference point. Second, to avoid a further decline in the spawning stock biomass. Third, to minimize the variability in catch. Fourth, to maintain the abundance of small fish. In order to identify the MP that is the most preferred management option, we need to establish some criteria for determining how the candidate management procedures are performing relative to these objectives. These criteria are called performance metrics. Performance metrics are quantitative measures of management objectives. They are typically expressed as the probability of achieving some desired outcome in a given time frame. For example, a management objective focused on ensuring the spawning biomass remains above some limit can be stated as: for a management procedure to be considered an acceptable candidate for management, there must be at least 80% probability that the spawning biomass is above the limit reference point within the next 5 years. In this case, the performance metric is the probability that the spawning biomass is above the limit reference point in the first 5 years of the projections. Any MPs that have less than 80% probability of achieving this are eliminated from the list of potential candidates. For the first management objective, we have the stated goal of rebuilding the spawning stock biomass to the upper stock reference point. We have 2 performance metrics related to this management objective. The first performance metric calculates the probability that the spawning biomass during the first 5 years of the projection period is above the limit reference point. The second PM calculates the probability that the spawning biomass is above the upper stock reference point. This PM is calculated over the first 10 years. Both performance metrics have a minimum acceptable probability of 80%. That is, any MPs that do not have at least 80% probability of rebuilding the stock above the limit reference point in the first 5 years and above the upper stock reference point in the first 10 years will be considered unacceptable candidates for implementing the fishery. The DFO precautionary approach policy suggests a limit reference point of 0.4 BMSY and an upper stock reference point of 80% of BMSY, and these are the values that have been used in this example. The second management objective is to prevent further declines in the spawning stock biomass. The performance metric corresponding to this goal calculates the probability that the biomass in each year is larger than the previous year. This is calculated for all years until the biomass first reaches the limit reference point. This PM has an acceptable probability of 95%, meaning that MPs that have greater than 5% probability of the biomass declining are not considered acceptable options. The next management objective relates to the desire to minimize interannual variability in the catch. 2 performance metrics are calculated for this objective. The probability that the average interannual variability in yield, AAVY, is less than 10% and less than 30%. These metrics are calculated over all years and no minimum acceptable probability has been defined. The 6th performance metric relates to the size composition of the catch. This metric is defined as the percent of small fish in the catch, where small fish are defined as those less than 23 centimeters in length. Similar to the previous PM, the probabilities are reported, but no minimum acceptable probability is defined for this metric. We now have our set of 24 reference operating models and our list of 6 example management procedures and are ready to run the MSC. In this presentation, we will just focus on the first reference OM. This table shows the results for the first performance metric, the probability that the spawning stock biomass is above the limit reference point in the first 5 years of the projection period. The plot on the right is a projection plot showing the biomass relative to BMSY for the 6 management procedures. The solid black line shows the median and the 5th and 95th percentiles are showing the grey shaded area. The status quo MP has a 97% probability that the spawning stock biomass in the first 5 years is above 40% of BMSY. The 3 index target MPs perform even better, with close to 100% probability that the biomass in the first 5 years is above the limit reference point. Perhaps not surprisingly, the MP with the TSE is fixed at 75,000 tonnes has a lower probability of the biomass remaining above the limit reference point. The projection plot shows that the biomass tends to decline quickly to very low levels with this MP. Finally, the no fishing MP results in the biomass rebuilding well above the limit reference point and the upper stock reference point. The MPs have similar performance for the second metric. the probability that the biomass is above the upper stock reference point of 0.8 BMSY within the first 10 years. Again, all MPs except for the fixed TAC MP exceed the 80% minimum acceptable probability. Therefore, in this example, the fixed TAC MP will be eliminated from further consideration, and the trade-off will be examined for the remaining MPs to determine which is the best suited for this fishery. In this operating model, the biomass started well above the limit reference point, and therefore this performance metric is not applicable in this case. There is considerable difference in performance for the MPs with respect to the performance metric calculating the probability that the average interannual variability in yield is less than 10%. The status quo MP very rarely meets this criterion, highlighting that the TAC is likely to be variable if this MP was adopted. 3 index target MPs had a maximum change in TAC coded into them, and use a smoother to remove some of the variability in the acoustic index. Consequently, these MPs have a higher probability that the TAC varies less than 10% between years. It may be surprising that the MP with a constant TAC of 75,000 tonnes has a low probability that the average interannual variability in catch is less than 10%. This is because this management procedure resulted in many years where the TAC was too high for the amount of available biomass, and the actual catch taken in the model was much lower than 75,000 tonnes. With the exception of the fixed TAC MP, where the stock crashed in many cases, all MPs had greater than 85% probability that the TAC varied less than 30% between years. Finally, the last performance metric shows the average percent of small fish in the catch. The status quo MP had the largest percent of small fish, while the 3 index target MPs had slightly fewer small fish. This trade-off plot shows the average annual catch on the y-axis and the stability and yield metrics on the x-axis. The fixed TAC MP would not be considered a suitable candidate as it fails to meet the minimum performance criteria. The first 2 index target MPs, iTarget 1 and iTarget 2, would also likely not be considered suitable candidates. These MPs both have lower expected catch compared to the other options, with iTarget 2 having significantly greater variability in yield as well. This leaves the status quo MP and the 3rd index targeting MP, iTarget 3. There is a clear trade-off in the outcomes for these MPs. Status quo results in the highest expected catch, but has greater variability in the catch. iTarget 3 has lower expected yield, but is much more stable. Due to the limit on the amount that the TAC can change between years that's hard-coded into this MP, the TAC never changes by more than 10%. So far, the results have been calculated for only one OM, the first OM from the reference set. The MSC will be applied to each of the 24 operating models, and the performance of the MPs compared across the range of OMs. For example, while the index target MPs all performed very well with respect to the first and second performance metrics, for the first OM, the results are quite different for reference OM number 10. This OM assumes a different scenario for the growth pattern of fish and assumes a less resilient stock with lower steepness of the stock-recruit relationship. The status quo and index target MPs all meet the minimum requirement for the first performance metric. However, all 4 of these MPs failed to meet the second requirement of 80% probability of rebuilding the stock above the upper stock reference point within the first 10 years. This suggests that more management procedures need to be developed that are capable of rebuilding the population under the conditions assumed in this operating model. This is something that we discussed in the next steps of the project, as well as continuing to develop the performance metrics that will be used to evaluate the management procedures. We hope that this presentation has been helpful in demonstrating the process for the herring MSC. We look forward to discussing this with you at the next meeting.